Beneath the vast, silent expanse of our world's oceans, a hidden network quietly hums with the lifeblood of our digital society. This is not the realm of mythical sea creatures or lost cities, but the domain of subsea fiber optic cables. These are the unseen arteries that carry the internet across continents, connecting people, connecting economies, connecting cultures. Every time you send an email, stream a movie, or make a video call overseas, you are likely using this incredible infrastructure. The story of how these cables are placed on the seafloor is a saga of immense engineering, precision, and human ingenuity. A journey we will explore in From Seafloor Up. It begins long before a single inch of cable touches the water. The sheer scale is almost impossible to comprehend. Over 1.4 million kilometers of fiber crisscross the seabeds, enough to circle the Earth more than 35 times. This web carries over 99% of international data. Satellites matter, but cannot match the volume, speed, or reliability of fiber. The journey of a subsea cable begins not at sea, but in a quiet office filled with maps, charts, and powerful computers. This planning phase can take years, balancing cost, safety, and performance. Marine engineers and surveyors choose the safest, most efficient path, sometimes over thousands of kilometers. They start with bathymetric charts, seeking a route that avoids major obstacles. Steep underwater mountains, active volcanic zones, deep trenches, and earthquake-prone areas are hazards to avoid. A flat, stable seabed is ideal, but rarely perfect in reality. Once a preliminary route is set, the real exploration begins. A specialized survey ship sails the entire proposed path for a detailed investigation. Multi-beam echo sounders bounce sound off the seafloor to build precise 3D maps, revealing ridges, canyons, and hidden features. Sub-bottom profilers penetrate sediment to show sand, mud, and rock layers, crucial for predicting burial feasibility. Core samples are taken and analyzed, determining whether a plow can cut through soft sand or if rocky ground demands extra care. These findings guide tool selection and cable type for each segment. Surveyors also plot existing infrastructure and protected habitats to avoid conflicts and minimize impact. They factor in weather, currents, tides, and navigate complex regulations. After mapping, sampling, and negotiation, the final route is approved. With the route finalized, attention turns to the cable itself. A subsea fiber optic cable is both delicate and rugged, a marvel of material science. Hair-thin glass fibers carry laser pulses, ones and zeros, at terabits per second across oceans. Fibers are cushioned in gel to resist shock and moisture, then housed within a sealed metal tube that also conducts power. Power feeds repeaters, amplifiers spaced along the route, to keep signals strong until they reach shore. High-strength steel wires add tensile strength, so the cable can be lowered and lifted without snapping. Armor varies, garden hose thin in the deep, heavily armored near shore to resist anchors, trawlers, even the rare shark bite. A tough polyethylene skin adds waterproof, abrasion-resistant protection. Built to protect light for 25 years or more, the cable works silently in the dark abyss. These fibers are why intercontinental internet feels instant. Repeaters ensure clarity across vast distances. Billions rely on this rugged strand of light every day. Once the cable is manufactured and the route is set, the operation moves to port, where a specialized vessel readies for sea. These purpose-built ships are engineered for stability and precision. Dynamic positioning, GPS, thrusters, and propellers, lets the ship hold station within a meter, even in wind and current. Cable is spooled into giant tanks in a slow, methodical loadout that can take weeks. Every coil is guided by hand, because mistakes now can become disasters at sea. Cable engines control speed and tension. Massive sheaves guide the cable cleanly overboard. ROVs and a sea plow stand ready for placement and burial. A multidisciplinary crew manages navigation, machinery, and fiber handling. They review the route, program navigation systems, and test every winch, sensor, and engine. Provisioned for weeks or months, the ship departs carrying years of planning and the promise of a new connection. At the shore end, The cable is connected to a landing station, floated ashore on buoys, and hauled into place by beach teams. The ship advances at walking pace, paying out cable through tensioners and over the stern sheave, every meter monitored from the control room. In deep water, cable is laid directly on the seabed, where the cold, high-pressure environment is stable and undisturbed. Engineers model payout speed and tension to avoid suspended spans or seabed loops. Closer to shore, human activity, trawlers, anchors and construction, demands burial beneath the seabed. A heavy sea plow is towed along, cutting a 1 to 2 meter trench, placing the cable and letting sediment fall back to cover it. In soft sand or mud, ROVs use high-pressure water jets to fluidize sediment so the cable settles into a temporary trench before it closes. Live video from ROVs lets engineers verify perfect placement and burial in real time. Kilometer by kilometer, the line grows across the ocean floor until continents are joined. Laying the cable is a milestone, but the work isn't over. Testing begins on shore and continues at sea. Engineers monitor fibers with OTDR, sending light pulses to confirm integrity and localize issues. Final commissioning measures loss, signal-to-noise and latency, critical for finance, gaming, and everything in between. Repeaters are verified, and the cable is integrated with terrestrial networks under live traffic observation. After proving stability and reliability, the system is commissioned. Another digital highway lights up between continents. A cable's life includes constant monitoring and sometimes urgent repair. Most faults come from human activity, trawlers and anchors, with some from landslides and strong currents. OTDR pinpoints the break. A repair ship holds position, grapples the cable, and brings ends aboard. Technicians fusion splice hair-thin fibers, seal the joint in armored housings, and lower the cable back, reburying if needed. Their vigilance keeps the unseen arteries healthy, so the world can live, work, and connect. Underwater fiber optic cables are complex systems that enable global communication by transmitting data as light signals through optical fibers. Here's a simplified overview of how they work. Key components: optical fibers, thin glass or plastic fibers that transmit data as light signals. Repeaters, undersea devices that amplify the light signal to maintain signal strength over long distances. Cable structure, a robust, layered structure that protects the optical fibers from the harsh underwater environment. How it works. 1. Data transmission. Data is converted into light signals and transmitted through the optical fibers. 2. Signal amplification. Repeaters amplify the light signal at regular intervals to counteract signal attenuation. 3. Data reception. The light signal is converted back into electrical signals at the receiving end. Underwater cable structure, fiber optic core, contains the optical fibers that transmit data. Strengthening fibers provide mechanical strength to the cable. Insulation protects the optical fibers from water and pressure. Armoring, steel wires or other materials that protect the cable from damage and abrasion. Advantages: high bandwidth. Fiber optic cables can transmit vast amounts of data at high speeds. Low latency. Signal transmission is relatively fast, with latency as low as 60–70 ms for transcontinental connections. Reliability. Modern underwater cables are designed to be highly reliable and resistant to damage. Challenges: installation and maintenance. Laying and repairing underwater cables is complex and expensive. Seabed obstacles. Cables must be carefully routed to avoid underwater obstacles and hazards. Security. Underwater cables can be vulnerable to tampering or damage, which can disrupt global communication networks. Overall, underwater fiber optic cables are critical infrastructure for global communication, enabling the transmission of vast amounts of data across oceans,